Hello everyone, can you hear me? Okay, I'm going to be reading about operating systems again. And later today, I have a plan to learn some basic Japanese. That would be in the later stream and it will be on my language learning channel. So if you guys want if you guys want to see me learn Japanese, like the very basics of it, I would stream it. I'm planning to stream it later today. Anyways, I'm going to be reading about operating systems. And last stream, I read about concurrency bugs. We learned about the ordering violation, I think. Yeah, the ordering violation. And there was another violation, I forgot. The deadlock one. No, not deadlock. Yeah, there were two types, non deadlock bugs and deadlock bugs. Within the non deadlock bugs, there was ordering violation or atomicity violation. Yeah. Anyways, um, this stream I'm going to be reading about event-based concurrency, and if I'm in the mood, I will also read multi-CPU scheduling. I remember I had to read this after reading about concurrency. So, okay, let's start this. Let's start with this chapter. Thus far, we have written about concurrency as if the only way to build concurrent application is to use threads. Like many things in life, this is not completely true. Specifically, a different style of concurrent programming is often used in both geo applications as well as some types of internet servers. This style is known as event based concurrency, has become popular in some modern systems, including server side frameworks such as Node.js, but its roots are found in Unix systems that we'll discuss below. The problem that event based concurrency addresses is twofold. First is that managing concurrency correctly in multi-threaded applications can be challenging, as we have discussed. Missing logs, deadlock, and nasty problems can arise. The second is that in a multi-threaded application, the developer has little to or no control over what is scheduled at a given moment in time. Rather, the programmer simply creates threads and then hopes that the OS, underlying OS schedules them in a reasonable manner across available CPUs. Given the difficulty of building a general purpose scheduler that works well in all cases for all workloads, sometimes the OS will schedule work in a manner that is less than optimal. And thus we have the crux. How to build concurrent servers without threads. How can we build a concurrent server without using threads and thus retain control over concurrency? I'll just open Excalibur. The basic idea in event loop. The basic approach we will use as stated above is called event-based concurrency. The approach is quite simple. You simply wait for something to occur. When it does, you check what type of event it is and do the small amount of work it requires, which may be including issuing IO request and or scheduling some other event for future handling, etc. That's it. Okay, something just came up. I will have to end the stream early, so I will only just finish this chapter then. Anyways, so wait in like a web server, like in a Node.js application. I have a question. So if you have a Node.js application, let's say in a Node.js you have a func one, right? And then you have, yeah, let's say in some Node.js application you have func one, and then on the client side, you're calling fetch This is an API endpoint. Call it. Let's say next.js. You're calling it um uh, get data raw.ts. This is in Next.js. This is an API endpoint, and you want to call func1. So when there are two clients, for example, you have a client here, you have a client here. They make a fetch to func1 to receive the data, and then client 2 also makes a fetch. So does the server create like two threads? Does the server create like two threads, one for this fetch and another for this fetch? Or does it wait sequentially? Does it wait like return to first client and then return to second client? I want that question answered. Before getting into the details, let's first examine what a canonical event-based server looks like. Such applications are based around simple construct known as an event loop. Pseudocode for an event loop looks like this. So events, get event, for E in events, process event. It's really that simple. The main loop simply waits for something to do, and then for each event returned, processes them one at a time. The code that processes each event is known as an event handler. Importantly, a handler processes an event. It is the only activity taking place in the system. Thus, deciding which event to handle next is equivalent to scheduling. This explicit control over scheduling is one of the fundamental advantages of the event-based approach. But this discussion leaves us with a bigger question. How exactly does an event-based server determine which events are taking place? In particular, with regards to network and disk I/O. Specifically, how can an event server tell if a message has arrived for it? With that basic event loop in mind, I mean, next must address the question of how to receive events. In most systems, a basic API is available by either the select or poll system calls. What these interfaces enable a program to do is simple. Check whether there is any incoming IO that should be attended to. For example, imagine that a network application wishes to check whether any network packets have arrived in order to service them. These system calls lets you do exactly that. Take select, for example. The manual page describes the API in this manner. So select, read, write, error, timeout, and whatever this is. The actual description from the man page, select examines the IO descriptor sets whose addresses are passed in read FD. What is FDS? Read FDS, write FDS, error FDS to see if some of the descriptors are ready for reading, are ready for writing, or have an exception condition pending, respectively. The first NFTs descriptors are set in check. The descriptors from 0 through NFTs -1 in the descriptor sets are examined. On return, select replaces the given descriptor sets with subsets consisting of those descriptors that are ready for the requested operation. Select returns the total number of ready descriptors in all of the set. Blocking and synchronous interfaces do all their work before returning to the caller. Non-blocking interfaces begin some work but return immediately, thus letting whatever work that needs to be done get done in the background. The usual culprit in blocking calls is IO of some kind. For example, if a call must be read from disk in order to complete, it might block, waiting for IO request that has been sent to disk to return. Non-blocking interfaces can be used in any style of programming, but are essential in event-based approach, as a call that blocks will halt our progress. A couple of points about select. First, note that it lets you check whether descriptors can be read from as well as written to. The former lets a server determine that a new packet has arrived and is in need of processing, whereas the latter lets the service know when it is okay to reply. The outbound queue is not full. Second, note the timeout argument. One common usage here is to set the timeout to null, which causes select to block indefinitely until some descriptor is ready. However, most robust servers will usually specify some kind of timeout. One common technique is to set the timeout to 0 and thus use the call to select to return immediately. Both system call is quite similar. See its manual page. Either way, these basic primitives give us a way to build a non-blocking event loop which simply checks for incoming packets, reads from sockets with messages upon them, replies as needed. To make this more concrete, let's examine how to use select to see which network descriptors have incoming messages upon them. Figure 33.1 shows a simple example. This code is fairly simple to understand. After some initialization, the server enters an infinite loop. Inside the loop, it uses the fd0 macro to first clear the set of file descriptors or file descriptors. That's what it means. And then uses fd set to include all of the file descriptors from minimum fd to maximum fd in the set. The set descriptors might represent, for example, all of the network sockets to which the server is paying attention. Finally, the server calls select to see which of the connections have data available upon them. By then, using fd is set in a loop, the event server can set which of the descriptors have data ready and process the incoming data. We have main, and then this is the main loop. So fd set variable set to 0. Now set the bits for the descriptors the server is interested in. For simplicity, all of them from min to max. fd, so fd set. So all of the descriptors are set to 0. Do the select, rc select. Check which actually have data using fd is set. Of course, a real server would be more complicated than this. This requires more logic to use when sending messages, issuing disk IO, and many other details. For further information, see Steven and Rago for IPA information for a good overview of the general flow of event-based servers. Event-based servers enable fine-grained control over scheduling of tasks. However, to maintain control, no call that blocks the execution of the caller can ever be made. Failing to obey this design tip will result in a blocked event-based server, frustrated clients, and serious questions to whether you read this part of the book. With a single CPU and an event-based application, the problems found in concurrent programs are no longer present. Specifically because only one event is handled at a time, there is no need to acquire or release logs. The event-based server cannot be interrupted by another thread because it is decidedly single-threaded. Thus, concurrency bugs common in threaded programs do not manifest in the basic event-based approach. Thus far, event-based programming sounds great, right? You program a simple loop, handle events as they arise. You don't even need to think about logging. But there is an issue. What if an event requires that you issue a system call that might block? For example, imagine a request comes from a client into a server to read a file from disk, return its contents to the requesting client. To service such a request, some event handler will eventually have to issue an open system call to open the file, followed by a series of read to read the file. When the file is read into memory, the server will likely start sending the results to the client. Both the open and read calls may issue IO requests to the storage system when the needed metadata or data is not in memory already, thus may take a long time to service. With a thread based server, this is not an issue. While the thread issuing the IO request suspends, other threads can run, thus enabling the server to make progress. Indeed, this natural overlap of IO and other computation is what makes thread based programming quite natural and straightforward. With an event-based approach, however, there are no other threads to run, just the main event loop. And this applies that if the event handler issues a call that blocks, the entire server will do just that. Block until the call completes. When the event loop blocks, the system sits idle and thus is a huge potential waste of resources. We thus have a rule that must be obeyed in event based systems. No blocking calls are allowed. To overcome this limit, many operating systems have introduced new ways to issue IO requests to the disk system, referred to generically as asynchronous IO. These interfaces enable an application to issue an IO request and return control immediately to the caller before the IO has completed. Additional interfaces enable an application to determine whether various IOs have completed. For example, but how does this happen? Like, does the IO processing happen in another thread? For example, let us examine the interface provided on a Mac. The APIs revolve around a basic structure, the struct IO AIOCB or AIO control block in common terminology. A simplified version of the structure looks like this. File descriptor, file offset, location of the buffer, length of transfer. To issue an asynchronous read to a file, an application should first fill in this structure with relevant information. File descriptors of the file to be read, the offset within the file, as well as the length of the request. And finally, target memory location into which the results of the read should be copied. After the structure is filled in, the application must issue the asynchronous call to read the file on a Mac. This API is simply the asynchronous read API. The AIO read, struct AIOCB. This call tries to issue the IO. If successful, it simply returns right away and the application can continue with its work. There is one last piece of the puzzle we must solve, however. How can we tell when an IO is complete, thus that the buffer now has the requested data within it? One last API is needed. On a Mac, it is referred to as AIO error. The API looks like this. The system call checks whether the request referred to by AIO CBP has completed. If it has, the routine returns success. If not, an EIN progress is returned. Thus, for every outstanding asynchronous IO, an application can periodically poll the system via a call to AIO error to determine whether the said IO has yet completed. One thing you might have noticed is that it is painful to check whether an IO is completed. If a program has tens or hundreds of IOs issued at a given point in time, should it simply keep checking each of them repeatedly or wait a little while first? To remedy this issue, some systems provide an approach based on interrupt. This method uses Unix signals to inform applications when an asynchronous IO completes, thus removing the need to repeatedly ask the system. This polling versus interrupts issue is seen in devices too, as you will see in the chapter on IO devices. Systems without asynchronous IO, the pure event-based approach cannot be implemented. However, clever researchers have derived methods that work fairly well in their place. For example, Pi et al. Describe a hybrid approach in which events are used to process network packets and a thread pool is used to manage outstanding IO. Read their paper for detail. Another issue with the event based approach is that such code is generally more complicated to write than traditional thread based code. The reason is as follows: when an event handler issues an asynchronous IO, it must package up some program state for the next event handler to use when the IO finally completes. This additional work is not needed in thread based programs, as the state the program needs is on the stack of the thread. Aria et al. Call this work manual stack management, and it is fundamental to event based programming. To make this point more concrete, let's look at a simple example in which a thread based server needs to read from a file descriptor, and once complete, write the data that it read from the file to a network socket descriptor. The code looks like this. So read, and then Okay. So, and this is the return code, right? So read this file descriptor, buffer size, and then write it to a network socket. As you can see in a multi-threaded program, doing this kind of work is trivial. When the read finally returns, the code immediately knows which socket to write to because that information is on the stack of the thread. In an event-based system, life is not so easy. To perform the same task, we would first issue the read asynchronously, issuing the AIO calls described above. Let's say we then periodically check for completion of the read using AIO error, AIO error call. When that call informs us that the read is complete, how does the event-based server know what to do? The solution, as described by Adia et al., is to use an old programming language construct known as continuation. Though it sounds complicated, the idea is rather simple. Basically, you got the needed information to finish processing this event in some data structure. When the event happens, when the disk IO completes, look up the needed information, process the event. In this specific case, the solution would be to record this socket descriptor in some kind of data structure, example hash table, indexed by the file descriptor. When the disk IO completes, the event handler would use the file descriptor to look up the continuation, which will return the value of the socket descriptor to the caller. At this point, the server can then do the last bit of work to write the data to the socket. What is still difficult with events? Yeah, I will read that at the end. There are a few other difficulties with event-based approach that we should mention. For example, when systems move from a single CPU to multiple CPUs, some of the simplicity of the event-based approach disappeared. Specifically, in order to utilize more than one CPU, the event server has to run multiple event handlers in parallel. When doing so, the usage synchronization problems arise and the usual solutions must be employed. Thus, on modern multi core systems, simple event handling without logs is no longer possible. Another problem with event based approach is that it does not integrate well with certain kinds of system activities such as paging. For example, if the event handler page falls, it will block and thus the server will not make progress until the page fall completes. Even though the server has been structured to avoid explicit blocking, this type of implicit blocking due to page faults is hard to avoid. This can lead to performance problems when prevalent. Third issue is that event-based code can be hard to manage over time as the exact semantics of various routine changes. For example, if a routine changes from non-blocking to blocking, the event handler that calls the routine must also change to accommodate its new nature by ripping itself into two pieces. Because blocking is so disastrous for event based servers, a programmer must always be on the lookout for such changes in the semantics of the APIs each event uses. Finally, though, asynchronous disk IO is now possible on most platforms. It has taken a long time to get there. It will never be quite, it will never quite, and it never quite integrates with asynchronous network IO in as simple and uniform a manner as you think. For example, while one would simply like to use select interface to manage all outstanding IOs, usually some combination of select for networking and AIO calls for disk IO are required. We have presented a bare bones introduction to different styles of concurrency based on events. Event-based servers give control over scheduling to the application itself, but do so at some cost and complexity and difficulty of integration with other aspects of modern systems. Because of these challenges, no single approach has emerged as at best. Thus, both threads and events are likely to persist as two different approaches to the same concurrency problem for many years to come. A huge and fascinating infrastructure known as signals is present in all modern Unix variants. At its simplest, signals provide a way to communicate with the process. Specifically, a signal can be delivered to an application. Doing so stops the application from whatever it is doing to run an a signal handler. Some code in an application to handle that signal. When finished, the process just resumes its previous behavior. Each signal has a name such as hang up, interrupt, segmentation violation. See the man page for details. Interestingly, Sometimes it is the kernel itself that does the signaling. For example, when your program encounters a segmentation violation, the OS sends it a pre-pending sig to signal names. Wait, the OS sends it a segv. Pre-pending sig to signal names is common. Sig segmentation violation. If your program is configured to catch that signal, you can actually run some code in response to this erroneous program behavior. When a signal is sent to a process not configured to handle a signal, the default behavior is enacted. For SegB, the process is killed. It is a simple program that goes into an infinite loop but has first set up a signal handler to catch signal hang up. So handle stop waking me up. Signal hang up. Doing nothing except catching some signals. You can send signals to it with the kill command line tool. Doing so will interrupt the main while loop in the program run the handler code handle. There is much more to learn about signals, so much that a single chapter, much less than a single page, does not nearly suffice. As always, there is one great source, Stevens and Rago. Read more if you're interested. Okay, I kind of rushed through this chapter, but like I still want to know how the asynchronous works in terms of threads. Like, does it create a new thread, or does like the IO does its stuff? It creates a asynchronous, so it's a single threaded, non-blocking program, right? This I'm assuming is asynchronous input output control block. But it's not clear to me how does it asynchronously read the file. If it's single threaded, how is it doing two things? Okay, I will research that on my own. Should I read the summary? I wanted to read this chapter as well, but I have to go somewhere in a little while, so that's why I'm cutting short. So does your head hurt now? Okay, professor. So does your head hurt now, student? Well, it's hard to think about all the ways threads can interleave. Professor, indeed it is. I am always amazed when concurrent execution is involved. Just a few lines of code can become nearly impossible to understand. Student, me too. It's kind of embarrassing as a computer scientist not to be able to make sense of 5 lines of code. Professor, oh, don't feel too badly. If you look through the first papers on concurrent algorithms, they are sometimes wrong. The and the authors often professors. What? And the authors are often professors. Yes, student, professors can be wrong. Professor, yes, it is true. Though don't tell anybody. It's one of our trade secrets. Student, I am sworn to secrecy, but if concurrent code is so hard to think about and so hard to get right, how are we supposed to write correct concurrent code? Professor, well, that is the real question, isn't it? I think it starts with a few simple things. First, keep it simple. Avoid complex interaction between threads and use a well-known and tried and true ways to manage thread interactions. Student like simple locking and maybe a producer consumer queue. Professor, exactly. These are common paradigms and you should be able to use to produce the working solutions given what you have learned. Second, only use concurrency when absolutely needed. Avoid if at all possible. There is nothing worse than premature optimization of a program. Student, I see. Why add threads if you don't need them? Professor, exactly. Third, If you really need parallelism, seek it in other simplified forms. For example, the MapReduce method for writing parallel data analysis code is an excellent example for achieving parallelism without having to handle any of the horrific complexities of logs, conditional variables, and other nasty things we have talked about. MapReduce sounds interesting. I've read more about it on my own. So good. You should. In the end, you will have to do a lot of that, as what we have learned together can only serve as the barest introduction to the wealth of knowledge that is out there. Read, and read some more, and then try things out. Write some code, and then write some more. Practice more too. Beyond what's in the books, there are plenty of other resources out there. As Galvin talks about in his book, Outliers, you need to put roughly 10,000 hours into something in order to become a real expert. Can't do all that of inside of class time. Student. Wow. I'm not sure if that's depressing or uplifting, but I will assume the latter. Get the work. Time to write some more concurrent code. Okay, then I will end the stream here. And yeah, next stream I will read that last chapter. I want to finish that one chapter, and then I will stream on the other channels. Okay, anyways, see you guys next time. Bye.